Okay, we can use this structure to prove a mathematical result that we deduced mathematically before. So say we send some state, it can be unknown, it can be known, it doesn't matter, into a Stern-Gerlach apparatus, and let's say it's in the z direction, also doesn't matter. So let's call this state psi, unknown. We split it into its two parts, but we're going to recombine them. Now, we haven't actually done anything, right? Because we haven't blocked either of these beams off. We separate the spin polarizations, but then we recombine them. Now, remember that it's amplitudes which are relevant in quantum mechanics rather than probabilities. We can add the amplitudes back together and we get the original state. So this just gives us our original state back. We haven't performed a measurement. Before, when we block one of the beams, we're effectively performing a measurement by saying if it's gone past here, we know that it must be spin up in Z. We're not going to do that now. So in the intermediate state, we have up in Z here, and the amplitude for that state must be, it was initially in psi, and it was finally in up in Z. So it was initial psi, final up in Z. And similarly down here, this would be in state down in Z, initially in psi, final state was down in Z. And so we find that since this psi equals this psi, we must have that. The state psi, this one over here, has to be the initial psi, which is the same. The amplitude of that to be up in Z multiplied by the state up in Z, plus the amplitude for it to be down in Z multiplied by the state down in Z, because it's either this or this. For classical probabilities, we would add the two options. Here it's amplitudes which add rather than probabilities, so we get this. And I've rewritten the amplitudes to the right of the states. But now I can factor out, I can see that everything multiplies a psi on the right, so I can rewrite this. So psi is equal to up in Z outer product up in Z plus down in Z outer product down in Z, and this whole thing acting on psi. And since this is true for any psi, doesn't matter which, it must be the case that this object here is just doing the job of the identity matrix. And so we have the final result. The identity matrix is equal to up in Z outer product up in Z plus down in Z outer product down in Z. You can check it explicitly in the basis where up in Z is 1, 0, down in Z is 0, 1. But actually you can deduce it just using the results of these experiments, which is very nice. And so this is the resolution of the identity, which we deduced mathematically before. And here we're just relying ultimately on the fact that this structure has our observables, the values of the spin, as the eigenvalues of Hermitian matrices, non-degenerate Hermitian matrices, and those non-degenerate Hermitian matrices must have complete orthonormal bases of eigenvectors. Explicitly, you can write it as follows, using this particular choice of basis, and you can check it for yourself, and you can also check it works for the spins in the x direction and the spins in the y direction. Okay. Earlier on in the course, when we were dealing with wave functions, which we will return to later, we looked at expectation values of things like the position and the momentum. We can look at expectation values of spin operators as well, and we get something like this. That is the expectation value of the operator SI, so this is the spin in the I direction, x, y, or z, evaluated for state psi. We can just write this in Dirac notation as the matrix for SI acting on ket psi sandwiched with bra psi. So it's like a bracket with the operator sandwiched in the middle. And so it's another convenience of Dirac notation. The expectation value, we tend, even in statistics, subject separated from quantum mechanics, we would expect to write the expectation value with these angled brackets. And so by construction now, the mathematical operation we do to find it is built into the notation. So that's very convenient. So in particular, we could evaluate the following. The expectation value of the Sz operator, the spin in the z direction, for an eigenstate of the Sz operator is just given by the operator acting on up in z just gives h bar over 2 acting on up in z by definition. That's how we constructed the mathematics. and so this evaluates to h bar over 2, the eigenvalue, which hopefully makes sense. If we were look instead at this, the expectation value of the spin x operator for a state which is up in z, we know we must get the result 0, because there's an equal probability of up in z giving the value up in x as there is down in x. It must always give one of those results because that's the measurement that's being performed. And you can check this structure mathematically, and we'll do that in the problems. Okay, thank you for your time.